All right, chapter 2 review guide. For geometry. All right, so for the first page, it is a lot of written multiple choice. I'm not going to write the whole thing here, but I will make sure that I write the correct answer. So the number 1 through 4, we are looking at conjunctions and disjunctions. Are they true or are they false? So January is the first month of the year and December is the 10th month of the year. That's number 1. Really quick though, let's look at conjunction. So a conjunction, this would be something good to have. Either you can write it, oh yeah, y'all looked at front and back, either on separate notebook paper. You might be able to fit it on the off to the side if you have small handwriting. But a conjunction, what word denotes a conjunction? And. So it's an and. What's the symbol for conjunction? Yes, it's like an upside down V, or it's like an A with capital A with no dash across from it. So these both denote conjunction. Now, how do you know that whether a conjunction is true or false? Does anybody remember this? It's been a hot second.
If the hypothesis and the conclusion are true.
Yes. So, or both simple statements. So yes, both simple statements must be true. So for a true conjunction, both simple statements must be true. And if you remember from the truth tables, like if you had P and Q, if it was a conjunction, if the conjunction of P and Q, if P was, what is it? True, true, false, false, and then true, false, true, false. I am saying false, funny, aren't I? False?
Yeah.
Okay, false. Then the conjunction is only true when they are both true. And I can't draw to save my life. It's so bad. It's so bad. Whatever they're doing upstairs is kind of making me emotional too. So those are all false. All right, disjunction. What word represents a disjunction? Or what is the symbol? That's the V is the symbol. And a true, just what makes a true disjunction?
One or the other. So
Yeah.
P is true or Q is true.
So at least one statement is true. Then the disjunction will be true. So again, you put that in a truth table, P disjunction Q. Oh, so bad. I cannot even with myself. That one and that one. 2, 4. Okay, so true. Nope. One more. True, false, and false. True, false, true, false. So these are all the possibilities. Then the disjunction, this one's true, this one's true, this one's true, and that is the only one that would be false. All right. All right. So now that we've gone over conjunction and disjunction, number 1 says January is the first month of the year and December is the 10th month. So is this a disjunction or conjunction? It's conjunction. Is it true or false? Why? Right. The second one is false. So this is number 1 will be B. It is a false conjunction.
Wait, what? That's number 1?
Uh-huh.
Oh, I thought we were still talking about.
So what about number 2? 2 plus 3 equals 6, or 4 plus 7 equals 10.
Neither are true.
Right, they're both false, therefore it is false. So that's what, D? False disjunction. All right, number 3 is the sum of 2 even counting numbers is even, and the sum of 2 odd counting numbers is even. So we have a conjunction or disjunction. We've got a conjunction. Is it true or false? So if you are adding 2 numbers, are they always 2 even numbers? Are they always even? Yes, every time, right? So how about odd? 7 plus 3. 3 plus 5. 13 plus 3.
16.
Right, so they're always even. The only time you get an odd number in a sum is when you add an odd number to an even number. It will always be odd.
I feel like we've done this before and it was wrong and we didn't think that it was wrong. But
There was a lot of confusion originally with conjunction and just, I kept getting confused about the symbols.
the charts is what.
But in this case, they're both true. They make more sense now. Progress is good. So this is a true conjunction. All right, and what about number 4? So 4, red means go or red means stop. It's a true disjunction because red does mean stop. So this one is C, a true disjunction. I mean, it's supposed to. All right. So for number 5, 6, 7, I think that's as far as I went for right now. So for these, you need to remember about converse, inverse, and contrapositive. So let's look at that for a second. What does converse mean? It's reversed. So in a converse, you reverse your conclusion and your statement and your hypothesis. So converse is reverse.
This was on chapter 2.
Yeah,
This feels like it's been forever.
it has been. Y'all slow. Just kidding.
We are just not finishing chapter 2.
We kind of had this big Christmas break right in the middle of it, which makes it seem like it's been a year in one chapter. That's why it feels like it's so long. All right. Inverse means what? Not quite opposite, but negative. So that means you negate both your statement and your hypothesis. So this is the negate. And then contrapositive. I remember that. I told y'all to. Anything from chapter 2, keep it all together and keep it until we take the chapter 2 test. Same thing with chapter 3 and chapter 4. Depending on how far we get. Contrapositive means you both reverse it and negate it. Okay, so let's look at what we've got here. So for number 5, it says, which statement is the converse of the conditional? If it snows, then school will be canceled. It's B. If school is canceled, then it snowed. Do you see how that just reversed the 2? So that is the example of a converse. Number 6, the inverse of if it snows, then school will be canceled. A, if it does not snow, then school will not be canceled. And then number 7, what statement is the contrapositive? If it snows, then schools will be canceled.
If school is not canceled, then it did not stop.
There we go, C. So it's C, if school is not canceled, so we've moved school be canceled to the first part and we've negated it, then it did not snow. Okay, So these other three are the modus ponens, modus tollens, and transitivity. So we have, let's see, modus ponens is the first premise would be P, if P then Q. The second premise is P, and therefore the conclusion says therefore Q. So if P then Q, P is true, therefore Q is true. Modus tollens. You're saying your premise, the first premise is the same. If P, then Q. Your second premise is negative Q. And so your conclusion is negative P. So if P, then Q, but Q is not true, or the opposite of Q is true, therefore the opposite of P is true. And then transitivity, something like that, is the one that I like the best because we use it I use it a lot in algebra. It says that premise 1 is P, therefore if P then Q. Premise 2 is if Q then R. So the conclusion is, I always forget the therefore, sorry. Conclusion is therefore P, if P then R. All right, so looking at number 8. So number 8 says, if the team plays well, then they will win. So P is the team plays well, Q is the team wins. Will win. The team did not win. That's what? Negative P. Did I negate the first part or the second part of the first statement? We negated the second part, which is Q. So we have premise 1 is P if P then Q. The second premise we have is negative Q. Therefore, the team did not play well. So what is this an example of? Modus tollens. I did start this back up, didn't I? Yep. Okay, good. Just checking. Number 9. If you study hard for a test, then you will get an A. So P is studying hard for the test. Q is getting an A. You did study hard for a test. Therefore, you got an A. Modus ponens. Everybody see that? If P then Q, premise 2 says P is happened. Therefore, Q happens. All right. 10.
We have already had this question.
Oh, yes, we have. Some of these were from my test bank.
Okay.
So I'm pulling them from previous quizzes. I'm pulling them from, y'all may not have seen them on previous quizzes, but I might have used them to make a previous review guide. But these are the closest thing to being applicable to what you're also going to see on the test. No, the test bank has like 150 questions, but there's only like, I think 25 on your test. And then I picked 35 additional ones, something like that. It's close. It's a lot. All right, 10, identify the type of argument. All Christians are stewards. All stewards have responsibilities. Therefore, all Christians have responsibilities. Yes. If P then Q, if Q then R, therefore if P then R. So that is C. Okay, good. Okay, there is something else I want us to look at. This is from page, well, I'm going to give you a couple examples. Page 73, exercise, example 3. There's something else that they really just didn't have a work for that is on the test, and it is assuming the converse and assuming the inverse. So I want to give you guys, this is not exactly example 3. That's another example, but it would be a really good example to put on a note card or somewhere in your notes that would be easy to find. But this one also, example 3 would be one to look at. This one also should help you out as well. So let me show you something. Premise. Okay, let's try it. ISE. So if we have premise 1, I almost spelled promise, says if it rains today, this is not any, you are going to want to write this down somewhere. If it rains today, of course, you are also going to have a video, so go back and reference it if you want. The dam will break. This you don't have in your book, and you don't have it on your review guide either. I found it later to kind of help us out. Premise 2 said it did not rain. So the conclusion says the dam did not break. Now, do you think this is an example of assuming the converse or assuming the inverse?
Curious.
What are we working with here? Are we negating it or are we reversing it? This is assuming the inverse. All right. So the basic premise addressed only what would happen if it rains. But there are other factors that could cause the dam to break. So we are assuming that just because it did not rain, that the dam did not break. Now, the proper, let me just, this is not assuming the inverse. I can show you like a correct, like a valid logic for this. So again, let's say premise 1 is the same. If it rains today, the dam will break. Premise 2, it rained. Therefore, your conclusion is what? The dam broke. This is a valid argument using, it looks like modus ponens. So you see how if the premise negates the first simple statement, that you can make the mistake of assuming that negates the second simple statement. So you get an invalid conclusion. So this is invalid because you were assuming that if it didn't rain, the dam won't break, but it only told you that it will break if it rains. It could still break if something else happens. So the only thing you can have a valid conclusion on is that if it rains, the dam will. Okay. All right. So let's look at assuming the converse then. So again, we have the same premise. Premise 1, if it rains today, the dam will break. Premise 2 tells us the dam broke. So the incorrect conclusion,
Is it cannot rain.
well, the incorrect conclusion would be it rains. But something else could have broken the dam,
Wait,
not rain.
that's the incorrect conclusion?
This is incorrect. This is assuming
Oh, okay.
the converse.
I know what you're saying.
So we are assuming that if the dam breaks, that means it rained. But something else could have made the dam break. It might not have rained. So the only thing that we can gain from our first premise, if it rains today, the dam will break, is that it rained. Therefore, your correct conclusion is the dam broke. But assuming the converse is invalid, just like assuming the inverse is. Okay, can we see that?
I don't like this left brain stuff.
Oh, the left brain stuff. You are left brained.
Huh? I'm not left brain.
I'm a right.
Aren't you right-handed?
Yeah,
Then you use your left brain.
it's not true.
Yes.
That is not how that works.
That is exactly
Oh,
how that
I'm
works.
not left.
All right, there's one other thing that we are. Let me just see. I think, you know, what, let me just give this to you. It is definitely part of the same section. Biconditional. Y'all are still being recorded, aren't you?
I hope so. Oh,
Face reveal.
face reveal. Guys, what's it 50 likes for a face reveal?
Oh, viewers.
Turn the camera on us.
Do y'all just enjoy silent lunch? Or is this, yeah, I mean, I would. Let me see here. Okay, no, yeah, we're good. Okay, biconditional is written as if P, then Q, and if Q, then P. And it is stated as P if and only if Q. An example would be coplanar lines do not intersect if and only if, that's awful, they are parallel. So this is what you want to look for. I think on the test, you're just identifying a biconditional. So having your notes available will be helpful. Okay, so let's move on to the properties of properties of addition, properties of multiplication, and the properties of equality, which should put us close to 2.4 or 2.5 in the book. So for number 11 through 14, name the property illustrated. So for number 11, we have 2/3 times 3/2 is equal to 1. So that's an example of what property?
That would be the associative property of multiplication.
Not quite. Associative property involves order of operation. It is the inverse property. It is the inverse property of multiplication. This is a multiplicative inverse. An example of an additive inverse would be 12 plus -12 equals 0. But this is 2/3 and 3/2 are reciprocals of each other. When you multiply reciprocals and the answer is 1, then you have multiplicative inverse. If you are adding, your answer is 0. You're adding the opposite, not the inverse. Okay, 12 is 2 plus 3 is equal to 3 plus 2. Commutative, very good. So remember, the commutative changes the order of the numbers, but it's telling you no matter what order you move them in, you can still add them up to get the same answer. So this is your commutative, which I think in that case is
I
B.
know the next one.
You do?
This is the identity property of addition.
All right, we have an additive identity. Any number plus 0 is equal to that number, which is D, identity. This is the additive identity. An example of the multiplicative identity. Do we multiply numbers by 0 to get the same number? We gotta multiply them by 1. So an example would be like 3/8 times 1 is equal to 3/8. That's the multiplicative. Identity. So just remember, multiplication is 1, addition is 0. All right, last one for this section, number 14. We have, which is not a property of an equivalence relation. What are the 3 properties of an equivalence relation?
Equivalence.
Mhm.
They gotta be equal.
So make sure you know the definition of an equivalence relation.
Okay, so they have to be symmetric,
Yes,
okay? They have to be reflexive,
yes,
and they have to be transitive.
and they have to be transitive. Yes. So the answer is identity. They do not have to, you don't have to add a 0 or a 1. So equivalence relation must be symmetrical, transitive, and what was the other one? Reflexive. Now, this is not all the definitions, theorems, and postulates you're going to need, but this is a few of them. Name the definition, postulate, theorem, or property that justifies each statement. So 15 states that if AD is congruent to BG and BG is congruent to MN, then AD is congruent to MN.
That is the transitive.
Mm-hmm. You remember that? Now that you said it out loud? Right. Okay, so 15 is transitive. So make sure if you've got the transitive property on a note card, this might be a great example to put on there for it. So that's transitive property. If AD equals BG and BG equals MN, therefore AD equals MN. That is an important property. We use that a lot in proofs.
We can use this on the test, yeah.
Yes,
Clarifying.
yes.
Six-
16 says if M is the midpoint of XY, then XM is congruent to MY. That's the definition of a midpoint. The midpoint tells you that if that point is a midpoint, that the 2 line segments created by it are equal or congruent. 17, if TU plus UV equals TV, then TUV, T dash U dash V.
Is that the definition of congruence? Between this.
Between this, very good. Don't forget between. That's what this is showing. This means between. That means that T, U, and V are on one line. T is here, U is here, and V is here, and they are not necessarily the same distance apart. It's not a midpoint, but we know that TU plus UV is equal to TV, so that's between us. Okay. Oh, I think we can get through these properties. Most of these are algebra properties, so they should, for the most part, still be review, although I'm finding it's a big review. All right, so match the property illustrated by each statement, and it renumbers itself, which is always fun. So the first one says 5x equals 35. If 5x equals 35, then x equals 7. What property did we use to go from 5x equals 35 to x equals 7? What do you think, Gabe? What did we use to get x equals 7? Well, it was multiplication, but what did we do to both sides of that equal sign to get x equals 7? Right? By 5. And what happens what do we call it when we have to use a property on both sides of an equation? Nope. That usually has more to do with parentheses. Anytime when you solve algebraic equations, you use properties of equality. So this is the multiplication property of equality. So it's G. Now, let me explain this in terms of a proof. Let me give you a statement. You have two statements here, and let me give you a reason. So if you have the statement 5x equals 35, let's say it's given. And then you have x equals 7. How did you just get from statement 1 to statement 2? The multiplication property of equality. All right. So the statements are the steps as you solve something. The reason is the mathematical reason that that step works every single time. So that's what you're looking at here. Okay, so let's look at the second one. The second one says if 3 times x plus 2 equals 2 times x plus 4, then 3x plus 6 equals 2x plus 8. Goodness. We do have that much fun in algebra.
That's so mean. That's actually impressive.
Then 3x plus 6 equals 2x plus 8. What did we just do? What did we just do, Gabe? We distributed. So what is this? Which is which one? E, yes. There you go. I was trying to make him feel better for the first one. He struggled. All right, I know. Okay, for 3, 7x plus, in parentheses, 4x plus 3 equals 7x plus 4x plus 3. So what is this one, Andrew?
Why would you?
Because you said you use this one. You've used this one before
I have.
incorrectly. So I'm giving you the chance to use it correctly.
That's positive.
Are you sure?
Uh-huh.
Wait.
You use this property for something else. And it was not the right property at the time.
Oh, obviously, then, that is the transitive property of equality.
No, you used that one fine. What did we just do?
We changed the parentheses.
Which means what? We changed what with using parentheses? Do you know, Aiden? Which one? Yes. Which one did we do first? We changed the order of operation. The associative property changes the order of operation. And it's important, right? You need to understand that because what are your like terms? Right. So you need to know that even if there's a parentheses there, you can add the 7x and 4x first and before you ever interact with the 3. I know it feels like a second. So this is the associative property of what? Addition. The associative property of addition. This is A. 'Cause we're
I didn't
changing,
even see that.
because you weren't looking at it. We didn't change, we changed which ones we were adding together. It also includes subtraction, right? Because subtraction is just adding a negative number. You know this? Okay. For, this will be the last one, then we'll finish this up next week. If 2x is equal to y and 3y is equal to 4z, those of you that have had algebra 2, this one should look familiar, which means I'm talking to my 11th graders. Then 3 times 2x equals 4z.
Ooh, that's cool.
What did I just, this, y'all, this one is so important because we use it all the time in our proofs. What did we just do? I'm recording, hold on. Okay. What did we, okay, look at these two. These are our two statements. And then all of a sudden we went here. What did we use?
We substitute.
There you go. It's the substitution property. Substitution, we use it all the time. Look at this in terms of a proof. So we have a 2-column proof. Our first statement is 2x equals y, given. 3y equals 4z, given. Then you can then take that 2x, plug it in for y. I don't know why you would, but whatever, it works. 2x, and then the 4z doesn't change. And the reason you can do that is substitution. But you have to state them as facts first, and then use those facts to solve a problem. And substitution allows you to do that. Okay, you guys are done. We'll finish this up next week.